Okay, I heard you guys are getting a free lunch. I thought that wasn't right. So I want you to earn it a little bit. Anybody recognize these people? I'll give you a hint. When they were about your age when the picture was taken.
Friedman is on the left.
Good, good. Give him the lunch. Anybody know any others? Did you recognize? None of them's Becker. Okay, we'll come to him later. George Stigler's in the middle. Yep. Last one's Paul Samuelson. They were all students here a long time ago. They were students. They were, you might say, working for the econometrician of the day. Henry Schultz was his name. Friedman literally was working for him. He had an annual salary to be the research assistant for Professor Schultz. And the others were taking Schultz's class, and he had them working. To give you a little context, you recognize that building? Before we were here, we were in Rosenwald. Before we were in Rosenwald, we were there. Before Social Sciences building, yep. Just down the other side of Pick from where we are now. So that's where they had their offices. If you go over there, now we use it as a janitor's closet, but they got to know each other pretty well that way. What do you think they were doing? What was he paying Milton Friedman to do and paying really with a grade these other two to do, and many other of our students at the time?
Collect data.
Nope. Not a bad guess, though. He's an econometrician. Invert matrices, pretty much by hand. They had a calculator to help with the actual arithmetic, but they had to, construct the matrix and don't ask me how to do it. They knew how to do it. But the point is, they lost their jobs to robots. You guys, none of you guys have a research assistant job where you invert a matrix by hand. I sure hope your econometrics professor is not having you do that maybe more than once so you can see what it's like. Now don't feel sorry for them. They all did quite well after this, after the robots took that over. And, but I want to make the case today that the jobs that you're doing, professors are having you do, you're going to lose those to robots too. Those are going to be automated very soon, and the day will come where if you do the kind of things the way you do them now, in your Econ 201 class or 203 class, we'll laugh. We'll laugh and say, can you believe they did that way? Because machines can do it, and machines actually can do it today. So the good news, I think, part of the good news, I don't see any faculty here. That's good. So we'll try to think about how long can we get the faculty to continue to think that human beings are doing the economics homework. Any guesses? I think we can fool them for at least 5 years, maybe more. So here's what I mean by automated reasoning. There's two parts to the definition, the reasoning and the automated. Now first, on the reasoning part, I mean deducing conclusions from assumptions. So you assume something and ask, okay, based on that, what can I assume? What can I conclude? In the artificial intelligence area, they have a somewhat more technical idea, and actually we're going to follow that idea closely. You won't recognize a lot of these terms yet. By the end of today you will, though. And they call it eliminating quantifiers from a problem. So that's the reasoning part. There's nothing automatic here yet. The reasoning you guys have been doing manually has been eliminating quantifiers. Maybe you didn't call it that, but you'll see that's what you've been doing. And the automated part is to do it on a computer. The computer is going to automatically recognize the problem that you give it as a quantifier elimination problem, and it will eliminate the quantifiers and give you the answers. And I will show you that today. Now what it can't do, just like the computers in George Stigler's day couldn't do everything. There's a lot of things computers won't do right away, and one of those things I think will be pose the problem or tell you what's interesting. So if I were in school, today I'm not, if I were in school I would focus on those things like understanding how to categorize problems, pose questions, figure out what's interesting, and leave the mechanical stuff for the machine. Okay, so I'm going to just start with a little demo. These are going to be items that would be on fairly easy homeworks in your classes. I've opened Mathematica here. And Mathematica right away can't do what I'm showing you. You need a package that I put together. It's on the internet. Anyone who has Mathematica and has internet can just type this geteconomicreasoning.com, and that would load up the extra tools that you need. Now in here we don't have time, but I have, I think as of today, 25 and growing list of examples. And you could click on that and it'll let you scroll through the examples and see how I did it. Has some also extra functions here that I'm going to use one of them today, so I'm going to click on that. But the main function here is called Theory Guru. And in Mathematica, any function that's in there, you just type question mark at the name of the function, and it'll give you a little help on how it works. And what you can see here is that it takes an assumption and a hypothesis, and it's going to tell you, can you conclude that hypothesis based on your assumption or not? That's what it'll tell you. Here I've started typing with the Theory Guru. You just put Theory Guru in some brackets, and it has a blank for putting your assumptions and a blank for putting your hypothesis. Here's a really, really easy one, probably too easy for any of your homeworks, but to get us started, we have two assumptions. One's that the price is positive and the other the quantity is positive. And we want the machine to tell us, oh, does that mean that expenditure is positive? Really easy, you already know that. The answer is going to be true, and for sure that's what it says. Now it doesn't always say true. I didn't just make a machine here that just says true to everything. It's got three things that it can say: true, false, or the students say uncertain. Have you guys taken those tests? True, false, uncertain tests? Well, uncertain is not quite rigorous enough for me, so I have this other label. But what these means is it's either, yeah, it's always true that if your assumptions are right, then your hypothesis is right. Or false means it's never true when your assumptions are right that your hypothesis is right. And the last one is, well, sometimes and sometimes not. And we'll see some examples of that. Okay, so here's an example you might have in a homework, not a real hard one, about excise taxes. Supply and demand analysis of excise taxes. I drew a picture here. You probably had these pictures in your class. You have a market for beer or cars or something, and we're going to have a tax in that market. Every time you buy, say, a can of beer, you have to pay a tax. And the question is, well, how does the tax impact the market? That's a question you ought to be able to answer the old-fashioned way, but we're going to do it with the machine. So we're going to start out by saying there's a supply and demand equilibrium where the quantity demanded equals the quantity supplied. And the other thing we're saying here is, guess what? The price that the sellers receive is different than the price that the buyers pay. And the difference is the tax. And that's what we mean by an equilibrium in a supply and demand market with an excise tax. So I'm going to, rather than typing, I get a little slowed down when I have to do brackets and stuff, so I just said equilibrium. And every time I type equilibrium, that means demand equals supply. So now what am I going to assume? What would you assume in your class? Usually you assume that demand slopes down. That's what this means. The slope of the demand curve is negative. Supply slopes up. Slope of the supply curve is positive. Now that's not enough. We also need to assume that, hey, we have an equilibrium without the tax and we got an equilibrium with the tax. Now the way you did that in your classes, you might not have noticed that, but the way you did it in your classes is you totally differentiated here. And the machine does that automatically. And this really, the way I think of it is, hey, we had an equilibrium without the tax and equilibrium with the tax. Both are equilibrium, and that's what that says. And what we want to know is, okay, based on that, can we say that the tax reduces the supply price? And in addition, can we say that it reduces less than dollar for dollar? So you put on a dollar tax, the supply price will go down, but it won't go down a whole dollar. What do you think? Is that true or maybe? This is one you ought to have memorized. Yeah, it's true. It's true, and the machine will get that correct. Okay, I have a game theory example here. I'll let you look at that later. I want to get to something more passionate. Because part of the idea here is we get passionate about things and it sometimes clouds our reasoning. The machine doesn't have that problem. So let's get into some somewhat more passionate question, and that's inequality. Everybody's passionate about inequality, and we want to start to ask the machine some questions about how public policy might improve inequality, make things more equal. You see this dot here? That's a dot product, which I'm sure you did in high school. So we're talking about vectors here. So in this setup, we can talk about a vector of everybody's income. And that vector could be 300 million people long, one entry for every person in America. Or you want to talk about the world, it could be 7 billion long, one entry for every person in the world. And what we mean by inequality is to say that, well, inequality is 0 when everyone's at the average. That's what no inequality is. And to the extent that people deviate from the average, that means inequality. And the greater the deviations, the more inequality we have. If you're not familiar, I thought some of you, maybe high school is a little bit far back. You don't remember how dot products work. Here's some examples. When you take this is a 4-element vector, not a 7 billion element, but you take the dot product of two vectors, it just says, okay, let's multiply the two first ones, then add that to the product of the two second ones, add that to the product of the two third ones, and so on. So that's what we're doing here. That's exactly the same way you learned it in high school. If one of the vectors were ones, we might see that later, that just means add everything up, because the multiplications just involve going to 1. Okay, so we tell the machine what inequality is. Now what's progressive policy? We're going to have a tax. Could be a regulation too, but it's the easiest to think of a tax. And some people are going to pay a positive tax and other people are going to pay a negative tax, meaning they're going to get money. And the question we want to think about, well, what is a progressive policy going to do? Well, hopefully it charges the tax to the rich people who are above the average and gives the money to the people who are below the average, at least on average. It's hard in a big country like America to get it exactly right. So, and that's what this dot product is saying. The fact that it's positive means when the people have income above the average, they tend to pay a positive tax, not person by person, but on average. And when the dot product, when this one is negative, people who are poor, below the average, they tend to receive a tax. So we'll put that in. And then I'm going to just define what I mean by average after-tax income. This means whatever income people have minus the tax they pay, which of course, for the poor people, hopefully is going to be negative. So we've got that in there. Now let's ask the machine, if we assume that, first of all, the average is just a number, not a vector. We don't need to worry about that now. But we assume that the tax is progressive. I mean, it has this feature. It's not negative, so that the rich people actually get money and the poor people have to pay. It's progressive. Can we conclude that inequality is less after we do this taxation than it was before we did the taxation? What do you think? On average, you're going to be having the poor people receive and the rich people pay. So you get less inequality from that or not? Any ideas? You don't know? Have you guessed that it's in your best interest not to answer? The answer is it depends. It depends. It could be that on average you're paying the poor. But it could be, that's just an average statement. It could be that actually you're taxing the very poor. Now more often you'll end up subsidizing the near poor. That's what this means. But how most of us think about inequality, it's worse to take $1 from the poorest of the poor than to take $1 from someone who's just a little bit below average. And that's what this definition of inequality and so many definitions say. And this can be a problem. One of my favorite practical examples of this would be not a tax but a regulation, that say the federal minimum wage. Now, there's a great argument to say the federal minimum wage harms almost everybody, but let's put that aside. Let's suppose the federal minimum wage was helping the below average people, say in Michigan or Kansas, something like that. And there's a lot of people in Michigan and Kansas, so that would count. But that the minimum wage actually harms people, say, in Puerto Rico. Which, by the way, most economists think that, because the Puerto Rican wage, if it weren't for the federal minimum wage, would be so far below the federal minimum wage that you just can't sustain employment in Puerto Rico with a wage that's out of whack. But that's the nature of the federal. The federal policy gets it right on average, but it's not getting it right in every case, like in Puerto Rico. And I would argue that the fact that the Puerto Ricans, people living in Puerto Rico, are the poorest of our poor, we ought to give extra weight to harming them. And that's exactly what this definition of inequality and so many definitions do. Okay, and the last one, I'm going to let your passions cool off a little bit, so we'll do econometrics. This is a regression, a two-variable regression. Say all the variables have mean 0 so we can get to the issues here. So your dependent variables y, your independent variables are x1 and x2, epsilon's your error term, beta 1, beta 2 your coefficients. So we're going to tell the machine, hey, you know, that's our regression equation. These are vectors, so this could be a regression with lots and lots of data. Y could be a very long vector, x1 a very long vector, and so on. And we're going to ask it, okay, give me the formula for the least squared regression slopes here. And it has that functionality. You just tell it what's on the left and what's on the right, and it'll spit out a formula. In this case, it's two variables, so the formula is not too bad, although it's not one I'd want to do by hand. That's the formula. This is the least squared regression coefficient on the first variable and the least squared regression coefficient on the second variable. So we've told it that. And then we're going to ask it some questions like, you know, is the coefficient we got on the first variable, right? We got two coefficients here. Is the first one going to be equal to beta 1? Is our least squares going to be unbiased? And in general, you know the answer is no, okay? But let's assume something more. First of all, let's assume that x1 actually has some variation. If x1 is just 0 for everybody in your regression, you're never going to get a coefficient on there. No good computer will do that. So here I've just assumed, hey, there is some variation in your x variable. You could actually run a regression. And then the next thing I'm going to assume, hey, x1 is uncorrelated with the error term. Doesn't mean the error term is 0 or the x1 is 0. It just means that on average there's no tendency when x to be high for epsilon to be high. So what's the answer here? We assume that x1 is uncorrelated with the error term. Can we be confident that it's unbiased? There's no passion here, so this is as boring as it gets, right? So you can answer it, right? Nobody knows? The answer is maybe. You can't be sure. What do you need to do to make sure, to find out what you need to guarantee on bias? We could explore some of these buttons, but we don't. You do that at home. Here's one thing you can assume. This would be sufficient. Assume that x1 and x2 are both uncorrelated with the error term. If you do that, that's enough. Then it's true. But just to say that x1 is uncorrelated with the error term isn't enough. And I can't tell you how many graduate students, professors who I hear talking about the regression, they say, look, I know my x1 is uncorrelated with the error term. So what? Not enough. When you have more than one variable, it's more complicated than that, and Theory Guru kind of brings that to your attention. Okay, so that's the machine. Let's open the hood a little bit. So there's really three terms I need to talk about this. One's quantifiers, which I mentioned already, and I said it's mysterious, so we're going to take away some of that mystery. Next one's a Tarski formula, and the last one's a cylindrical algebraic decomposition, or I'm going to say CAD because it's easier. So with quantifiers, there's just a symbol, think of it. There's just two of them. And you're either talking about, hey, I have an example, that's what exists means, or hey, this is true for everything. And that's what the for all means, or the universal quantifier means. And then a Tarski formula, this is the exact definition. I'm going to show you by example. You're probably not comfortable with Boolean and polynomial and that sort of thing, but let's look at it by example. By looking at the ones I already showed you, and let's see, hey, where's the quantifiers under the hood? Where's the Tarski formula? So this was our first really easy example. And under the hood, what it's doing is, first of all, writing that down. It didn't show us that it did that. It's under the hood. And in writing that down, the first thing it has to figure out is what are the variables in this problem. And it figured out that there's two of them. One's called price and the other's called quantity. And what it's trying to figure out is, does that hypothesis work for all numbers you could have for price and quantity that satisfy the assumptions? And that's the Tarski formula, which is below. And that says, hey, either expenditure is positive, or if it's not positive, and this little, maybe you haven't seen this before, these V's just mean or. If it's not positive, then it must be that our assumptions aren't holding. Either the price is not positive or the quantity is not positive. Maybe both, but. And then it eliminates quantifiers from this. It decides, and that's actually a technical term in the field, it decides whether this is true or false. It's either true or false. There's going to be no maybe here. Either it's true for every single price quantity number you could put in there, or there's an example where it's not true. So this one turns out to be true for every single example. And what's kind of neat about this is you would think about, well, to say for all numbers, that could take me a long time to try all those. Even a computer could take a long time to try all those. But the answer is you don't have to try them all to know that it's true for all. And we'll see that. So here's what I showed you before, the three things you can get out. Now we can understand a little better what does true mean. It means for all your variables. Any real number you could imagine, you put in there for your variables, the assumption is going to guarantee the hypothesis. And then what false means is, hey, we have a counterexample. I'm sorry, there is no example. Not only is it not true for all, but it's not true for any. So there does not exist a single variable where your assumption and your hypothesis are true at the same time. And then the mixed case, and that tends to be the one you get on the exams, right? Is that, yeah, we got an example where the hypothesis is true, but we also got an example where the hypothesis is not true. And that's what we saw, say, with the regression. Saying, okay, the x1's uncorrelated with the error term. Yeah, it could be unbiased, but it also could be biased. Either is possible. Okay, that's a two-variable example, pretty easy. The next one we did was a three-variable example. Again, it recognized here what the variables needs to have. The derivative is one variable, or the price impact is a variable, and then the two slopes are variables. And then our Tarski formula says, hey, either that price impact is between -1 and 0, or one of the assumptions fails. Either the demand slope isn't going down, the supply slope's not going up, or you're not dealing with an equilibrium point. One of those. And this is what, when I pointed out on the first slide, I said, the artificial intelligence people say, you've eliminated quantifiers. That's what's happening. The computer started with this. After it scanned your problem and wrote it this way, then the next step is to get rid of those quantifiers. True doesn't have any quantifiers, right? There's no backward E there. There's no upside down A. Is this true? And this is what quantifier elimination means. Okay, so these are all automatic. It's going on under the hood. Here's our inequality one. Now we got 6 variables. Before we had 2, then 3, now we got 6. And the Tarski formula is more complicated. But again, the eliminating quantifiers, if you eliminate the all quantifier, the answer is false. It's not true for all. If you eliminate the exist quantifier, the answer is, yeah, there is an example. And that's why we get this one. But again, quantifiers are gone. Okay, so I've partly begged the question here. I said, okay, the computer scans it, figures out the variables, does the Tarski formula, and eliminates quantifiers. That last part's kind of magic. Actually, a little bit more than kind of magic. So how does that work? So there's 2 results. One from Tarski. He's a mathematician from quite a long time ago, probably my great-grandfather's generation. And then another one named Collins, who's much more recent. So what Tarski said is, number one, there's a universal algorithm, meaning there's a machine or a recipe, whatever you want to call it, that always works. It always works on what? If you have a Tarski formula dealing with the real numbers, which all of our examples had that. And not only does there exist an algorithm that'll do it, but it'll do it in a finite number of steps. And it'll give you back no quantifiers. Quantifiers eliminated. And how did he prove that? He gave an example. He said, here's an algorithm. It's universal. It always works. It's actually a terrible algorithm to actually use, and I don't know of anybody who's ever used it. But it's an algorithm, and you can prove that it always works. You just may have to wait a very, very long time. And you don't need any problem-specific guidance here. So we didn't have to tell the theory guru, oh, this is game theory. Oh, this is supply and demand. Oh, this is about inequality, vectors, or whatever. We didn't have to do that. Because I'm not using Tarski's algorithm. I'm going to use another universal algorithm, but that's what it means. The algorithm always works. The second guy we need to pay attention to is Collins. And he made an algorithm called CAD that is much better than Tarski's. And that's pretty much what I'm using and others are using in this field. One exciting thing about CAD is they're making it better. So problems, even if computers don't get better, we're going to get better at CAD. We're learning more and more about it even today. Okay, so what's a CAD? How does that work? It's actually very intuitive. I'll give you a couple definitions, but then I'm going to show you kind of how it works. There are cells. That's one thing we need to understand. Idea of projecting and the idea of lifting. So let's talk about cells first. So this is an example of a Tarski formula, or 2 polynomials you might use for a Tarski formula. It's a circle and a hyperbola. And we could ask it things like, well, are all the points that are inside the circle also inside the hyperbola? And ask it questions like that. Now, when I've drawn it, it's easy to answer them manually, if you will. But let's do that. So the cells, there's 13 cells in this picture. There's 5 that are 2-dimensional, if you will, white areas. 1 here, 2 here, 3, 4, and 5. There's 6 1-dimensional ones, the green, orange, brown, purple, blue, red. And then there's 2 0-dimensional cells, if you want, the 2 dots. And what's nice about these cells, why we focus on them, is if you have any cell, the polynomials only have one sign. So in this cell, the circle polynomial is positive. X squared, x1 squared plus x2 squared is bigger than 4. And so is the hyperbola one. It's also positive. When you go into this cell, okay, now the circle one's negative. We're inside the circle, but the hyperbola one's still positive. So there's really only kind of 13 cases you got to keep track of. That's the idea of the cells. Now it turns out that this is impractical. For this example, it's fine because you can kind of stare at it. But one problem with this example is, how do you order the cells? Which one comes first? Now here you can just kind of stare at it and say, okay, I go over here, maybe I'd scribble it out, make sure I got that one. and go through until you scribbled everything out. But I showed you an example in 12 dimensions. What are you going to do there? How are you going to march through that? So Collins's idea was, let's actually make more cells. Let's draw some vertical lines in there. That adds to the cells. But then we can be systematic about it. We can say, hey, we're going to start in the left column, or he called it a cylinder, and we can go from bottom to top. Make sure we get them all. And we're done there. Go to the next column, bottom to top. And you can march through it systematically knowing you won't miss any. It's kind of tedious for a person, but a computer just eats that kind of thing for lunch, just marching through from left to right and top to bottom. Now let me be clear. To use a theory guru, you don't have to do any of this stuff. That's all happening under the hood. I'm just explaining to you what, in case you're wondering what goes on under the hood, this is what's happening. It's a lot like driving a car. So many of us drive cars and they have no idea how they work, and that would be fine. But if you were wondering, that's what's happening. So for example, if we're trying to think about, well, is everything that's outside the circle also inside the hyperbola? That would be, if we were just doing it manually, we'd say, aha, that's the blue area, that's what we need. But what Collins would do is say, no, let's chop this up. Put those cylinders in there and then go through. And in each cell, in each color, any one cell either be inside the circle or not. Everywhere in that cell is the same in terms of being, say, outside the circle. And same thing with the hyperbola. So this phase here of drawing in the lines, that's called projection. And then they call lifting, where you just march through the cells and say, okay, here's a cell. I know everything's the same in the purple, so I just got to pick one purple point and think about it. And once I got that one purple point, I got all the purple points and go through projection and lifting. So here's an example in 3 dimensions. A 3-variable problem. What Collins would do is say, okay, first let's draw the cylinders down to the floor. And then when we're on the floor, let's draw the cylinders over to the wall. And that would be a 3-variable example, and then 99 variables, he'd do the same thing. And again, this would have the feature that every one of your cells, you only need to look at one of the points and you know about all the other points in terms of how they relate to your Tarski formula. Okay, so we did this. Mathematica is doing CADs. What the theory guru is done for you is kind of take your economics talk and turn it into Tarski talk and then pass it to Mathematica to do the CAD. That's what's going on. A lot of you probably use MATLAB and Stata, but not Mathematica, right? Am I right about that? Too bad. Sorry, they don't do that. There's other software other than Mathematica. Mathematica does not have the monopoly, but in this room probably it does. So that's why you need Mathematica. If you go to help.economicreasoning.com, I give explanation for everybody on campus. How can I get Mathematica for free? You can get it for free. It's not hard. Just follow those instructions. Okay, we discussed these already. Okay, how complicated is this? Well, theoretically, it's double exponential in the number of variables, which is really bad. If you were at the theoretical bounds of these problems and you say double your variables, maybe it took 10 seconds to do it, and then you double your variables, could take all day, in theory. Now, there's some good news in theory about this. Number one, CAD actually does need more than we need to do. And this is one of the things that's ongoing in the research. Can we have an algorithm that does less than CAD, but at least does it quicker and still gives us what we want? And the answer is yes, in principle. But mathematicians got a little carried away here. These are both quotes from mathematicians. And these aren't quotes from like the 1930s or anything. They're from the last couple of years. And they're just doing the theory. For the most part, they're doing the theory, and they have some examples from high school geometry. And they said, you know what? Yeah, in principle you can do it. Thank you, Collins. But in practice, your computer will never do that. This is another different mathematician saying, more than 5 variables, forget about it. They're wrong. They're absolutely wrong. We just showed that they're absolutely wrong. My laptop, I don't know. I got a couple kids who are younger than my laptop. I mean, it's not hard. And part of what's going on is really economics problems aren't as tough as some of the high school geometry problems in this way. That's really why you guys are able to do them manually. That's part of what's going on, and part of it has been the progress in the algorithms. Okay. So the next question I get is, okay, I'm going to do my homework with this. How can I trust this machine? Maybe it'll lie to me. Maybe it'll make a mistake. I mean, the machine's programmed by people who make mistakes. I make mistakes. So what about that? Well, there's a couple pieces of good news. First of all, there's a lot of ways to tackle the problem while still using CAD. In fact, there's something like n factorial or 2n factorial. So if you have 12 variables, it's like a billion ways you can tackle the problem. Every one gives the same answer. So one thing that you could do is say, okay, I got a billion ways to tackle the problem. They're all supposed to give the same answer. Let me try 2 or 3. And if they all give the same answers, I can be more comfortable that there wasn't a software error or a coding error. So that's one thing that you can do. You can use other software. So you can run it on Mathematica and then run it, sorry, not MATLAB, sorry, not Stata. But I've actually helped with that. So if you say your theory red log, what it'll do is it'll take the previous model that it did in Mathematica and it will write a program that you can run on some other software. Maybe you want to check the program, but you cut and paste this into a program called redlog. It's got nothing to do with Mathematica. The people who wrote it are different people. Runs on a different type of software underneath. And so then you can, not only can you try tackling the problem different ways with Mathematica, but you can say, okay, Mathematica said true and redlog said true. What's the chance that there's a software error doing those? So, and then there's actually one other way, but we don't have time for is beyond the scope. Okay, so let me go back to something a little bit passionate. This is a picture of our labor market in the United States during the recession, the most recent recession. And I got 3 measures of labor here based on employment, based on hours. Guess what? The labor market got smaller. Okay? I don't know that anybody disagrees with that. The question is, why did it get smaller? Why do we have a lesser quantity of labor in 2010 or 11 than we did in 2007? I wrote a book about that, so I got something at stake here. And you can see this is the cover. I said, it's got something to do with labor market distortion, something that had to do with taxes. Really, the excise tax I showed you has an awful lot like that. Not everybody agreed with me. Here's a guy. Didn't agree with that. Okay. Now, both of us write lots of things about the data and everything, but I want to focus on an argument that the theory guru can settle, which is statements about how supply and demand works in theory. Okay? And here's what he said. He said, hey, if you, dummy Casey, okay, if you think that what's happened is that there's been a shift in supply, that's the main reason why there was a reduction in the quantity of labor, then you must conclude that wages go up. Okay, this is not a statement about data. Now later on he'll go on to show you some data, which he also cheated on, but this is a statement, and we can all agree, right? This is a statement on how supply and demand works. And it's a little more complicated than the statements I gave you guys earlier. So I'd have a tiny bit of sympathy if a student got this wrong. But let's have the theory guru work on it. So we're going to have a labor market supply and demand equilibrium. Okay, he's the one who talked about supply and demand. I talk about supply and demand. We're talking about supply and demand. The wage is involved with determining equilibrium, but there's also things shifting supply and demand. AD shifts demand, AS shifts supply. And of course I'll put that in. That'll be our equilibrium. That demand equals quantity supplied on the basis of W, AS, and AD. Now I'm going to talk about 2 we got to talk about two outcomes. One, what actually happened, 2007, 2010, actually. But the source of the argument here is what would have happened if demand hadn't shifted. That's what he and I don't agree on. He says if it was supply that's what's going on, demand hadn't shifted, I'm sorry. The argument is about what would happen, if demand hadn't shifted. So we'll call that hypothetical. So there's really kind of three equilibrium points we're going to look at. We're going to look at what it was in 2007, what it actually was in 2010, and what it would have been in 2010 if demand had not shifted. So what are we going to assume? Okay, demand slopes down, supply slopes up. If he disagreed with that, he should have mentioned that. So he didn't mention it. Implicitly, that's agreement. And then we just have to normalize. I didn't say what these functions are, so we've got to say, well, is AD shifting demand out or in? This is the normalization, so I say, okay, it shifts it out. Same with AS, shifts it out. We're going to assume that we got an equilibrium, 2007, 2010 actual, 2007, 2010 hypothetical. The hypothetical demand shift was nothing. And the actual supply shift was the same as the hypothetical. So the hypothetical we're looking at is, give me the same supply shift that we actually happened. Let's see what happened if demand hadn't shifted. Okay, so that's the setup. And what does Krugman assume, or he attributes to me as an assumption? He says, if you thought that most of the drop in the quantity of labor would have happened anyway, right? Here's half of what actually happened. And I'm saying the drop that would have happened would have been more than half of what actually happened, which means it's responsible for a majority. And I did say that. You got that part right. Then he says you got to conclude that wages went up in the real world. So that's the assumption. He doesn't buy this part. He's saying if you're Casey and you're dumb enough to believe this, then you got to believe this. I'm sorry, the machine doesn't allow me. Machine does not allow me to believe that. It says true for some, false for others. Now what the theory guru can do is generate us an example. You might have seen some of those buttons. So it's like, oh, it might not be true. Show me an example where it's not true, please. Here's an example. And there's actually a function in there where you can take the example and turn it into a pretty picture like this. So here's an example where there's 2007, there's 2010, that's quantity. But if demand hadn't shifted, if you'd stayed on that 2007 demand curve, still most of the quantity reduction would have happened. Not all of it, but most. And furthermore, the wage would have gone down. So the picture doesn't lie. You may think I tricked you by magical programming in the computer, but the picture doesn't lie. This is a valid supply and demand picture, happened to be generated by a computer that shows us, hey, even though most of the quantity shift came from supply, wages can still go down. Good, so let's conclude a little bit here. What does this mean for you guys? You're in school. Well, one thing is that the process of going from assumptions to conclusions is cheaper now. Machine will do it. So you should do more of this. Just like students today do a lot more regressions, matrix inversions, than students in Friedman's day did, you ought to be tackling more problems. And that would be a good way to learn, a lot of practice. I'm not saying you should never do it the manual way, same with matrix inversion. I'm like, hey, your algebra teacher tells you to do an inverted matrix, do what he says. It's good to see a couple times how it's done. But from then on, let the machine do it and practice other things. And you can do all kinds of things in here. You can add assumptions, take assumptions out, and try to think to yourself, well, what's going to happen if I add this assumption or that assumption? What else do I need to assume so that Krugman would be right about what he said? You can do things like that with a push of a button. And really, the practice ought to be in, how do I categorize a problem? Oh, we have a recession. How do I put that into a framework, an economic framework, and then leave the mechanical part to the computer? That's the kind of thing that I would practice. The other thing, you guys aren't to publishing yet, or maybe some of you have. The other thing I think needs to happen is that when you publish something, you put something in print, you ought to have the backup, the computer that shows you why it's true. And that'll eliminate a lot of ambiguity. It's just like the empirical economists do today. If you have an empirical conclusion, you're supposed to turn in your data set to the journal so that other people can work with it. Well, I think the future of economic reasoning is going to be, hey, here's my reasoning as the computer saw it. So to finish off with our very good friends Friedman and Becker, they were good at so many things, but one thing I admire them for is they could deal with some of the world's most important problems without letting passion cloud their reasoning. And probably since you're getting a University of Chicago diploma, you'll be pretty good at that too. But a machine can make it even better. The machine won't be clouded by the passion. And maybe you can do some of the things these two guys did. Okay, good. Thank you, guys.